Hi, welcome back. In previous videos, we were looking at the del operator and how the del operator can be used to calculate the gradient of a scalar field. And the gradient is one derivative-like operation that we perform in three dimensions. And so there are several derivative-like operations, and in this video we're just going to look at another one, which is called the divergence. So let us check that out. Alright, well, the divergence of a vector field A at point P is defined as the outward flux per volume as the volume shrinks about P. So that's quite a mouthful, but let's consider a volume, like a differential volume, and by that I mean a small volume, and inside the volume sits a point P, and this volume is inside a vector field A. So I don't want to draw too many arrows because I don't want to messy up this drawing, right? But there's a vector field A around, or and possibly through this volume. Now, one thing maybe we didn't say before, but we're going to say it now. When you have a volume like this, the direction of each surface, well, we did say that the direction is normal to the surface, but the direction of each surface is chosen so that the direction is outward of the volume. So, the front face here would be facing towards you, and the back face there would be facing away from you, and then below, okay, and the left face is facing to the left, like that. So this is the convention that we use. Again, when the for any surface, the direction is normal, but there are two normals to the surface. And when the surface encloses a volume, when we have a closed surface like this, the direction is chosen for each surface. The direction is chosen so that the direction is outward of that closed volume, that closed surface. Okay, so now we're talking about the divergence, and so I just want to I'm going to write it down, the vector divergence of A, so of that field at point P, so this is the point P there, is the outward flux per unit volume as the volume shrinks about P. Okay, so the divergence is a point idea. It's not really related to this volume. The volume is going to shrink towards the point. So what we're kind of measuring is the flux at a point. Okay, now going back to this idea of the surface area is oriented outwards like that. Outward flux is considered positive. That's the convention. So if this vector field comes out of that front surface, then that would be positive flux. So all this is chosen, these conventions are chosen so that when you do the dot product of outward flux with outward surface area, you get a positive number. So that outward flux is positive, inward flux would be negative. So if the vector field is going into the back face, then that would be negative flux through that area in the back. Okay, so mathematically then we can just write down what it is that we just wrote down in English. We would say div, or divergence, of A equals the limit as delta V goes to 0. So here's my delta V, this thing. As delta V goes to 0 of this closed surface integral A dot ds. So this integral of A dot ds is the flux, right? We talked about that before. And then I'm going to normalize it per unit volume. Okay, so the volume is actually going to drop out because we're taking the volume to zero. So it's not, the divergence is not related to the volume, it's related to that point. We're going to shrink the volume about that point. Okay, so here's the interpretation before we figure out how to calculate such a thing, because that looks pretty intimidating. So we have this point, and if we had a vector field like this, so this is just a different vector field that I'm drawing here. This is not related to this first picture, but suppose we had a point P and a vector field like that. It looks like kind of P is the source of this vector field, and we would say that this has positive divergence. So now if maybe this is vector field B or something, we would say that there's positive divergence. So the divergence of B is greater than 0 at point P. Okay, the arrows are diverging from one another. And if we had a point P and maybe we had a vector field C, that looked like this at point P, well, this is the opposite of diverging, right? This is converging. And it's true that the divergence of C is negative here. Inward flux at point P, right? Divergence of C is negative. And let me just give you the case, or a case, where the divergence is 0. Let's say here's our point P, and I'll just draw in red. Maybe we have arrows like this. And here's vector field D. Here's point P. So in this case, we would say it would turn out that the divergence of D is equal to 0 at point P, and that's because the arrows neither converge nor diverge. Okay, so that's the interpretation here, and this is actually going to be very useful in electromagnetics. So now let's actually worry about calculating this thing from the we're going to start from the definition, and then I'm going to show you a little trick later. So the definition is longer, but you get a sense of what this thing is actually telling you. So let's draw this XYZ plane, and suppose we had a differential volume that's right there at the origin, 0, 0, and so we have a back face. I'm not really particularly good at drawing these things. And then we have this, side, front. Okay, so here's our surface, not our surface, excuse me. We have a volume, we call it delta V, and we're going to say that point P is at the origin, and we're going to shrink this thing towards the origin. So we're going to call this dimension delta Y, right? Just a small change in the Y dimension. And we're going to call this thing here delta X, a small change in the X direction. And we're going to call this thing delta Z, a small change in the Z direction. All right. And we're supposing, I'm not going to draw the arrows, but we're supposing that this differential volume exists in some sort of vector field. So you can imagine arrows going through this differential volume. And I'm going to talk about the front of the box. So we're going to let a circle represent the front of the box. So that's the surface in front. And similarly, we're going to call 2 the back. And 3 is going to be the left face of the volume. So these are all the surfaces that make up the volume. 4 is going to be right, the right side. 5 is the top side, and 6 is the bottom. So I could label these in the figure, but I'm trying not to junk up my figure too much. Keep it readable. All right, now let's work on calculating the essentially the divergence, but we're going to pick this thing apart and we're going to calculate the flux first. So if I want to calculate the flux, I need to calculate this thing, the integral of A dot ds. And we're going to suppose that our vector field, we're going to keep it general, and we're going to work in Cartesian coordinates for right now. So we're going to say our vector field has some component in the x direction, some component in the y direction, and some component in the z direction. Okay, those components are given by ax, ay, az, uppercase. All right, so now if I want to calculate the flux, what I need is, and because each surface is two-dimensional, I need a double integral, and so I'm going to have to do a double integral around surface 1, a dot ds, plus, and I'm not going to write this out, but you get the idea, I'm going to have to go around surface 2, a dot ds. Yeah, let me write it out. A dot ds plus surface 3, a dot ds. And I'm not going to write these guys out. We're just going to go up to surface 6, a dot ds. So I'm picking this thing apart, surface by surface. I'm going to calculate the flux through each surface. Okay, now let's look at surface 1. Surface 1 is what I'm calling the front of this thing. All right, so I need a double integral around surface 1, through surface 1, a dot ds. So this would be equal to double integral surface 1, and I would put in a x, my vector field, right? Like this, dotted with ds. So now we bring in the concept of, what was ds in this case. So in the front, we ask ourselves, what is changing, or what are changing? So in the front, we've got z is changing, right? There's a delta z there. And also in the front, y is changing, so there's a delta y. So our ds vector is dy dz, and then remember the surface vector direction is outwards. So in this case, for the front of it, outwards is towards us in the x direction, ax. All right, so I look at this dot product, and remember we said about the dotting of the basis vectors and everything. The only thing that's non-zero here is when I distribute the dot product into ax, because ax dotted with ax is 1, ax dotted with ay is 0, ax dotted with az is also 0. So now all I really have is this term that I need to be worried about, and so I also will have dy dz times that, right? And so I also need to ask myself then, how are y and z changing? So that will help me set up my bounds of integration. So z is changing from, we put this thing at the origin. So z is changing from 0 to delta z. And how is y changing? Y is changing from 0 to delta y. And then again, now when I do the dot product, I get ax dy dz, like that. Okay, well that's great. That's constant, right? And this is the x, so this just integrates to ax delta y delta z. Okay, and then I evaluate this thing at delta x, right? Because the front face is at x, delta x. Delta x is not changing, or the front face is not changing x location. So now evaluate it at x equals delta x. Let me try to draw that in the figure. So this front face is right here, right? This surface is located right here. Well, what x value is that? That's in the plane delta x. So evaluated at delta x, I'm just going to write this like this. AX evaluated at delta x times delta y delta z. Okay, and we're going to come back to this. But I'm gonna try to, for brevity, for time purposes, I'm gonna try to make the argument that surface two is similar. Surface two is the back. So let us think about how the back would change. Notice that it's still, it's parallel to the front surface that we just did. So this calculation is nearly identical, except the differential surface vector points in the negative AX direction, and AX is evaluated at x equals 0 instead. So what we would get would be negative, again because the surface vector points into the page, out of the volume, and then we would evaluate at x equals 0 delta y delta z. Okay, that's what we would get for surface 2. All right, now let us consider the summation of those two things. So I'm just going to delete a little bit of this. I'm going to leave the definition of divergence up. Yeah, that should give me enough room. Okay. So let us consider now the summation. A dot ds surface 1 plus A dot ds surface 2. Eventually we need to add up the flux from all 6, but we're going to just look at these 2 for right now. And we get AX evaluated at delta x minus AX evaluated at 0 times delta y delta z. Right? Okay, now we're going to make the leap, and we're instead of showing you the details of surfaces 3 and 4 and 5 and 6, we're just going to make the leap, and we're going to say, similarly, when you take 3 and 4, which are parallel to one another, when you take 3 and 4, you get AY evaluated at delta y minus AY evaluated at 0 times delta x delta z. And when you take 5 and 6 added together, maybe try to guess, maybe pause the video if you want, but you get a z evaluated at delta z minus a z evaluated at 0 times delta x delta y. Okay? And I encourage you to, work those things out on your own. But I'm going to erase this work here. So now we have this integral. We would add all 3 of these things up. 1 here, this guy here, and this guy here. If we add all 3 of those up, then we have the flux through all 6 surfaces. So that means the divergence of A, going right by the definition, is the limit as delta x, delta y, delta z all go to 0, right? The volume goes to 0 because the volume is delta x times delta y times delta z of, and then I'm not going to rewrite it, but I'm going to put the asterisks here. Plus second asterisk plus third asterisks. Right? And so by that, that's just shorthand for me saying, you know, this equation here, or this expression goes here, this expression goes here, and this expression goes here. We're adding up all of the fluxes through each surface to get the total flux. All right, and then again, going by the definition of divergence, we're going to divide by delta V, which is delta x times delta y times delta z. Now, notice this will be equal to, I won't evaluate the limit yet. The first expression, or I guess not that, I'm going to need some more room here. Let me back up. Limit delta x, delta y, delta z goes to 0 of. So now notice when I plug in the first asterisk, I'm going to separate the fractions basically. I have 3 terms in the numerator, so I'm going to separate them. So when I take the first asterisk and divide it by delta x, delta y, delta z, the delta y, delta z cancel, right? So I'm left with ax at 0 divided by delta x. And then similarly, I'll have ay evaluated at delta y minus ay evaluated at 0 over delta y, and az evaluated at delta z minus az evaluated at 0 over delta z. And amazingly, and this is really neat here, you should recognize this. You should recognize this as a derivative, right? As the limit as delta x goes to 0, we've got ax evaluated at delta x minus ax evaluated at 0 divided by delta x. So that's the partial derivative with respect to x. And same thing here, or similar thing here. We've got delta y going to 0, and we've got this difference quotient in y. So this is the partial derivative with respect to y, and then really awesomely here we've got the partial derivative. That's pretty cool. So all of this is to say, where we're going with this is I'm going to make the claim that this is actually del dot A. Okay, that's the claim, that this divergence is del dot A. So why is that? Well, remember the del operator in Cartesian coordinates is ax times this, it's hungry, right? It's hungry. It's ax times the partial derivative operator plus ay times the partial derivative operator in y plus az times the partial derivative operator in z. And then when you dot it with a, and a we're saying is right here, so it's got an x component, it's got a y component, right? It's got a z component. When you carry out that dot product, you get the partial of a with respect to x plus the partial on ay with respect to ay plus the partial of az with respect to z. That is, you get exactly this thing, the divergence. Amazing! So, when you calculate the divergence of something, you don't use the definition now. You usually don't use the definition like we just did. That's the long way. What you do is you calculate this dot product, del dot A. So when you see del dot A, that's read del dot A, or it's read divergence of A. All right. So the divergence of A, just to be clear, is this thing. Okay, and it's a scalar, right? It's the amount of which the arrows diverge, or they well, you know what diverging means in the general sense. So it's a measure of how much these arrows are diverging at a point P. All right, excellent. So that was Cartesian coordinates. We can do the divergence of a vector field in cylindrical coordinates. So is this something you need to memorize? No, do not memorize this, right? I mean, there's only so many hours in the day, so much brain power that you can expend. Don't don't use your brain power memorizing these things. Know that they exist and know where to find them. So here is the divergence in cylindrical. Okay, so just some things to be concerned with here. Notice there's a row there, and then a 1 over row there, 1 over row here, and then the z is as you'd expect, because the z doesn't change when you go from Cartesian to cylindrical. And we can have the divergence of a vector field in spherical coordinates, so that would be 1 over r squared partial of r squared times ar plus 1 over r sine theta times the partial with respect to theta of a theta sine theta plus 1 over r sine theta dA, the partial of a phi with respect to phi. So this would be spherical. All right, and we'll have examples of how to apply these things to certain vector fields. Now, there is an important theorem related to the divergence, and that is called the divergence theorem that we're going to cover right now. So I am going to erase what I just wrote down. Again, you don't have to memorize that, but know that it does exist. Know where to find it. Okay, so the divergence theorem states the following: that the total outward flux of a vector field, A, through the closed surface, S, is the same as the volume integral of the divergence of A. So let's write that down in mathematics. The divergence theorem says that the total flux through a closed surface S is equal to the divergence integrated over the volume that's enclosed by S. Okay, this is the divergence theorem. Okay, so we're going to forego the proof of this guy. The proof is in your book, or it's in my notes. Okay, it's easily found. We're going to forego the proof for brevity. But I will say that the way you use this is that the left side of this guy will come up in a lot of physical situations, as we'll see in electromagnetics, and it's the right side that is more easily computed. So this comes up in physical situations. Okay, and this is easily computed, as you'll see in examples. All right, that's the divergence theorem. And finally, I want to talk about solenoidal there's a lot of construction going on outside my house right now. It's distracting. Solenoidal fields. Okay, a vector field is solenoidal if the divergence, excuse me, is equal to 0. Let me give you some examples. So these these two are solenoidal fields. This one does not diverge. The arrows just keep going straight. This one does not diverge either. The arrows just keep going circularly. Okay, so that was a lot, and hopefully you have some good understanding of vector divergence. You probably need to work out some of the examples in my example videos. But this is just the second of several types of derivatives that we're going to look at in vector with vector fields. So we've got some more coming up. We've got vector curl and the Laplacian coming up. So I'll see you then.